Okay, let's get started. First of all, thank you for allowing me to be absent last week. And as promised, I have a retroactive bribe for all of you. There was a request for haggis and a request for scotch, neither of which I could comply with. However, I did bring back Scottish toffee. I know there is something called toffee here in the US, but it is not the real toffee. This is the real toffee. I'll pass around both of them. They have different kinds in them. There should be one for everyone here. If anyone has any dietary restrictions, the ingredients are on the back. So help yourself to one and pass them along. Okay. Okay, while you're helping yourself to toffee and signing the attendance sheet, how did things go last week with Zemo and user testing? Okay, I don't know whether Zemo is ready for prime time yet, but I thank you for providing some feedback to Jeff and his staff. What did you get out of the process of user testing? We started to talk about it the week before I left. What were some impressions of user testing?
It's really important to have a lot of different types of people try the software so you get a wide range of responses.
Exactly, right? The main message of this course, right? Make sure that your users are diverse in experience and every other sort of physical and mental and cultural dimension we've talked about, right? Really, really important. What else did you get out of user testing? Anything you learned that you didn't know when we started talking about it the week before?
I think no matter how much we learn or we research in this class, there's just so many less than obvious things about user interface that once you actually start to do something where it isn't obvious.
Exactly.
It's really hard.
That's it, right? Once you start doing user testing, every time, no matter how much experience you have with software development, there are always these non-obvious things that are kind of obvious in retrospect, right? Once you start doing some machine learning with your lead motion, the minority of lefty data that we have is going to become important, which is obvious now that we've spoken so much about it, but not perhaps when I first told you about lead motion. Right? So a big part of what makes HCI different from standard software engineering, where you may be working on the back end of a system, in HCI you're working on the front end, which is the part that's in contact with a large number of diverse humans. There are going to be a lot of things that are non-obvious and non-intuitive. And what we're trying to learn about when we talk about the HCI design process is how do we engineer the way we design our HCI interface to capture a lot of those non-obvious things. Right? It sounds like a catch-22. How do you prepare for non-obvious things that are only obvious in retrospect? You got to go, there's certain things we can do about user testing that help us make those things that are implicit explicit. Okay, I hope you had a good experience being on the other side of user testing, because you will be the one subjecting your flatmates and your friends and family to your system in a few weeks' time. Again, thank you for allowing me to be absent on Friday. Hopefully you watched the lecture video and had a look at slides and were able to complete the quiz for Friday, which brings us to today, Monday, the 26th. We're going to talk a little bit about Deliverable 4 and 5. Actually, like the last time I was here, we'll probably spend the majority of time today talking about Deliverable 5. And if we have time, we'll finish off Lecture 5 and maybe move into Lecture 6. Okay. That's where we were, that's where we are, and where we're going as we continue on this week. We're going to continue talking about the HCI design process and trying to make some of these implicit, non-obvious interactions between people and computers explicit. Okay, so let's start with Deliverable 4, which, as you all know, is due tonight at 11:59 p.m. Any questions that I can answer for you? How are we doing with Deliverable 4? Yeah? Okay. This is one of the least painful of all the deliverables. I wish I could say the same thing about Deliverable 5. So let's spend some time talking about Deliverable 5. What we're going to be doing in Deliverable 5, and I already mentioned this I think before, is in Deliverable 4 you're setting up your KNN learner, your machine learning algorithm, and it's chewing through existing data, the iris data set, right? The bulk of the work in Deliverable 5 is you're going to leave your KNN learner more or less the same. You're going to rip out all of the iris flower data set, and you're going to plug in leap motion gesture data. So instead of your KNN algorithm trying to predict which of 3 species a given flower belongs to, your KNN learner at the end of Deliverable 5 is going to be trying to guess whether this is the digit 1 or something else. Okay, so I'm going to walk you through Deliverable 5 a little bit. Again, this one is pretty long and it's got a number of steps. So I want to go through sort of the top level intuition and some of the major challenges in Deliverable 5, and then obviously you can read this at your leisure. Deliverable 5 is due next Monday night. So we can come back to Deliverable 5 on Wednesday and Friday. A lot of what you're going to be doing in Deliverable 5 is manipulating NumPy matrices and vectors, right? Comma, colon, numbers, and so on. Which dimension, what's the length of that dimension? How do I grab even rows and odd rows? Slicing and dicing matrices and vectors. So we're going to do a little bit of work at the board here for a few minutes, and we're just going to sort of sketch out what all of these matrices and vectors look like. So let's start with Deliverable 4. So in Deliverable 4, in the iris dataset, the iris dataset is made up of 2 data structures, one matrix and one vector. What's stored in the matrix and what's stored in the vector in the iris dataset?
Wasn't the vector the class?
The vector contains integers, which are the class, right? Is it the 0th, 1th, or 2nd flower species? And the matrix is?
It was a series of rows containing 4 observations each for each flower.
It contains 4 features each. So iris contains the matrix called data. And this data is a matrix that has 1, 2, 3, 4 columns. And these columns correspond to the features, right? So feature 1 might be the length of the petal of the flower, and feature 2 might be the width of the flower petal. I think that's actually what it is, right? An observation is all of these 4 features taken together, right? You take a flower and you measure these 4 features, and that's an observation of that flower. So in data, we have 4 columns, and we had 150 observations correspond to 150 flowers that were actually picked in a field somewhere in France. Right? Okay, that's the matrix data. Then we had inside iris, we have the target vector, which is the target class, right? We're trying to figure out what species this flower belongs to. So it's a vector. We have just one column, and we also have 150 rows, right? So this might be this particular flower corresponds to this species, this particular flower corresponds to this species, and so on. Right? That's what you get out of the box from scikit-learn. What you're doing in Deliverable 4 is changing these 2 data structures into 4 data structures, 2 matrices, and 2 vectors. What are these 2 matrices and 2 vectors that you create in Deliverable 4? We were pulling data out of this and storing it into these 4 data structures. Everybody remember? What about the first set here? So in Deliverable 4, you're creating this one first and then this one. What was the first matrix and vector you create in Deliverable 4? And populate with data from iris.data and iris.target. The training set, right? So this matrix is called train uppercase X. So in Deliverable 4, 5, and henceforth, anything that has an uppercase is showing that it's a matrix. And then we also had train lowercase y, which is the training set, right? This is the thing, these are the two data structures that KNN digests and uses it to predict data in this matrix and this vector. What was this matrix and this vector called? The test, right? So we want to test how good our learner is, right? We train our learner on this stuff, and then we expose it to this stuff, right? This is the test or the final exam for our learner, right? Like a human learner. We give it a bunch of training data, and then we see how well it does on stuff it hasn't seen before. And this stuff has the same form, obviously, as the stuff that it's trained on. So we've got test uppercase X and test lowercase y. How do we pull data out of these two data structures and place it into these four data structures? So in data here, we have a total of 150 flowers, and we break this into 75 rows, so 75 flowers for training, and then an additional 75 flowers for testing. Yep. The odd and even rows, right? So if you place :2 in a NumPy matrix, it'll give you back every second row if you do this. And it will give you back, if we do this, it'll give you back every second column, right? So we were using this to pull out the odd rows and place them in train X. So we pulled out 75 flowers and put it into training. And then we took every odd row and placed that into test X, right? So we got all this data divided into 75, two sets of 75 flowers. And when we do that, we also do the same thing with the labels or the classes associated with those flowers. So we take all of the odd elements of target and place that into train Y. So we make sure that the feature or class, the class stays associated with its four features. And then we also take the even elements of target and place them into test Y, right? That's the bulk of the slicing and dicing you're doing with matrices and vectors in Deliverable 4. So far, so good? Okay. How do we know that we've done all this correctly? Well, your learner should be able to do well on the final exam, right? It should be able to predict better than 50% on the 75 flowers in the test set. What kind of prediction accuracies did you see when you got your system working in Deliverable 4? For those of you that have finished Deliverable 4. Sorry?
One was 93.
Pretty good, right? 93. Okay. So if we see a prediction accuracy of 0.33, right? That's not so good. It probably means that your learner is basically flipping a three-sided coin or rolling a three-sided die, right? It knows that there are three different kinds of flowers, and what do you do on a final exam if you haven't studied? You guess, right? You can guess intelligently by saying, I know there's three, so I'll pick one at random and guess. If you guess randomly, you should get a prediction accuracy of 33%. So if you get something considerably higher than that, then you know that your KNN learner is working. Okay. Now, how well is it working? That's where things get tricky, right? It depends on the quality of the data. It depends on your choice of K, right? This KNN algorithm, which we've talked about, is pretty intuitive. You have a point in feature space. So in this case, in this four-dimensional space, we have this point, which is a question mark. What's the species that this flower belongs to? We find the K nearest points in that feature space. What are the flowers that have the most similarly long petals and similarly wide petals and so on and so forth? And if K is too small, you don't have enough data to make a good prediction, right? You're maybe looking at just the closest flower, which would be K equals 1. If K is huge, if K is equal to 75, you're looking at all the flowers and you're just going to guess the majority label, right? What was the most common species of iris that was picked in this data set? So this is going to be a challenge in Deliverable 5 because you're going to be recording the data, and we, myself, the instructor, and the TA have no idea how clean that data is and what the prediction accuracy should be. So one of the things you're going to learn to do in Deliverable 5 is try and figure out, work backwards from the prediction accuracy of your learner to know whether your system is working well. Your code at the end of Deliverable 5 may run perfectly and not crash, but unbeknownst to you, it's not learning anything, right? So you need to be able to sort of debug your code working backwards from poor performance on the test data. And there's some hints in Deliverable 5 to help you do that. Okay, so that's the data structures that you're working with in Deliverable 4. Let's look now at the data structures you're going to be working with in Deliverable 5. What you're going to be doing in Deliverable 5 is brushing off your recording program from Deliverable 3. As you remember, you have your primary hand, which is signing something. Your secondary hand comes into view of leap motion, and then the moment your secondary hand leaves, it snaps a picture of all the 5 times 4 times 6, 120 numbers that describe that gesture, right? And stores it out to a data file. Okay. We're going to be changing that file so that now when you bring your secondary hand into view of leap motion, it's going to start capturing 1,000 frames of you signing the digit 1 or the digit 3 or what have you. And after it's captured 1,000 frames, the record program just ends. All right, so you're going to kind of practice, and you can see your virtual hand on the screen. You can see that it's capturing the fact that your 3 fingers are extended, so you know it's seeing the digit 3. You're going to bring your secondary hand, and you're going to move your hand a little bit like this. Why are you going to move your hand rather than just hold it still while you record 1,000 frames?
So it's got more data to work with from different angles.
Exactly, right? So if much later, when you have your system and it puts up the number 3, and the learner is trying to learn ASL digits, and they remember that this is 3, they might do this, right? Or they might do this, or they might do this, or they might do this. So we want to make sure that we get enough data. So what you're going to start doing in Deliverable 5 is looking at the back of Deliverable 5, and you'll see your name in a list here, and you've been assigned 2 digits. And what you're going to do in Deliverable 5 is train your KNN learner to predict whether you are signing the digit 8 or the digit 9. So in the iris data set, there were 3 classes, right, or these 3 species. To start with, in adapting our system over to gesture data, you're going to be training your KNN to just predict one of 2 classes. Are you signing 8 or are you signing 9? So far, so good? Okay. As you can see, I've assigned each of you a different pair of digits. Why? You can probably guess where we're going for Deliverable 6.
Put them all together.
You're going to put them all together. So the last step of Deliverable 5, you're going to be, your submission for Deliverable 5 on step 47 here is you're going to be typing in your prediction accuracy. So you're going to try and bump up your prediction accuracy to be much higher than 50%. So in this case, the learner has just 2 classes. If it's not working and it ends up just rolling or flipping a coin in this case, if you do it randomly, you can get 50% accuracy. You need to demonstrate to us that your learner is doing significantly better than 50%. This part of the course, we're going to do things on the honor system. We can't debug your code. You're just going to type in the prediction accuracy, and we're going to go from there. We're not looking for you to get 100%. If you do get 100%, something else is probably wrong, right? So somewhere significantly better than 50% and somewhere below 100% is fine. All right? Okay. You are also going to be submitting, along with just typing in those percentage accuracies, you're going to be giving us back 4 matrices, train M, train N, test M, and test N. And I'm going to go through what those 4 matrices are now. So far, so good? Okay. Okay, so here we go. So let's say I'm been assigned the digits 3 and 4. So for me, M is the first number that I've been assigned, and N is the second number that I've been assigned. So when I submit my solution to Deliverable 5, I'm going to be submitting 4 matrices stored in 4 files called train. Let's do it down here. Train 3, train 4, test 3, and test 4. Okay. So here we go. So this is not unlike what we had over here. Now, what is stored in train 3? I've just told you that you're going to record, and I'll use myself as the example here. I'm going to sign the sign 3, and I'm going to wave my secondary hand in, and I'm going to capture 1,000 frames of me signing the digit 3. And after the 1,000th frame has been captured, it's going to store that in a it's going to store that in a matrix and store it to a file. Later in Deliverable 5, you're going to read that matrix in and reduce it to a 2-dimensional matrix. The raw data is going to be captured in a 4-dimensional matrix. What are the 4 dimensions? So I assign 3 and capture 1,000 frames, and I store to a data file a matrix with 4 dimensions.
Each of the 3 locations in space, and then point to the frame.
Not quite. Remember this picture. Right, so we got 4 dimensions to this matrix. What are they? Here's 3 of them. Not what you're signing. We don't know that yet, right? All I've done in the recording part is I've just recorded 1,000 frames of this. We don't have classes yet. We're going back to Deliverable 3. So we haven't even got to the KNN learner part yet.
So one dimension is 1,000 frames.
1,000 frames, right?
And then another dimension is 1 finger, and then frame.
That's right. So your matrix is going to contain 1, 2, 3, 4. If you access a number in there, you need to put numbers or something in these 4 entries. In NumPy, the first dimension of the matrix is the one that marches down, which is the number of rows in your matrix, right? So this dimension here. Okay. As we can see in the picture here, each row in this 4-dimensional matrix corresponds to one of the 5 fingers. We have 5 rows. Right? The second number marches horizontally from left to right, which is the number of columns. And this matrix has 4 columns, which represent the 4 bones in each of the 5 hands. Right? So element ij is going to give me back 2-dimensional matrix, which is all the information about the jth bone, in the ith finger. So each row is storing information about a finger, each column, 1 bone in that finger, and the third dimension, marching from the front to the back, is storing what information?
Like base, X, Y, and Z.
Exactly. So if you look at this picture, you can see that there's 6 stacks going from the front to the back, and each stack is storing information about one of the 6 numbers describing the position of the jth bone in the ith finger, right? The 6 numbers, the first 3 is what is the beginning position of that bone, and the second set of 3 numbers is the ending position of that bone. So the first 3 numbers give back 5 times 4 times 6 equals 120 numbers, which tells me everything I need to draw the hand, right? And as mentioned, the 4th number is now going to range between 0 and 999. So there's going to be 1,000 of these cubes, where each cube is one of the 1,000 frames. So I'm going to capture 1,000 frames of hand data, and it's all going to be stored in a single 4-dimensional matrix. I warned you, right? Lots of slicing and dicing of matrices in these deliverables. Okay, so the first part of deliverable 5, I sign 3, I go like this, I go like this, my program ends, and I now have a file that is storing a single 4-dimensional matrix that contains all the numbers that were captured when I did this. So far, so good? That's part 1 of deliverable 5. Part 2 is you're now going to read that 4-dimensional matrix back in, and we're going to do some training on it. And we're going to do some machine learning on it. Okay. In part 2, I apologize, I misspoke. It's not going to read in just one 4-dimensional matrix. It's going to read in 4 of them. And those 4 4-dimensional matrices are going to be reduced down to 4 2-dimensional matrices. Okay, what are these 4 4-dimensional matrices? Let's go through this again. I've been assigned the numbers 3 and 4. So I sign the digit 3, stores out the first 4-dimensional matrix, which is the training data for digit 3. So I've given the computer training data for digit 3. Then I sign the digit 4, and I've already forgotten what the digit 4 is in ASL. You'd think I'd know this after teaching this class a few times. There's 4. So the program ended. It saved all the training data for digit 3. I now sign the digit 4 and run the program again and generate 1,000 frames of training data for the digit 4. So I've now saved to 2 files, 2 4-dimensional matrices. So far, so good. Given it some training data for 3 and some training data for 4. I now go back and sign 3 and record another 1,000 frames of the digit 3, which is going to be used to test how well my KNN learner has learned to distinguish between 3 and 4. 4th and final time, I start up my program, I sign 4, and record 1,000 frames of me signing the digit 4, and it saves that to a file. Okay, sorry, so I didn't explain this fully. At the end of phase 1, you should have 4 4-dimensional matrices saved to disk, training data for digits 3 and 4, and testing data for 3 and 4, or whatever your 2 digits are that you've been assigned. Okay, step 2 now is we're going to have our other program, the classify.py, which you're writing for deliverable 4. You're going to convert this now so it can deal with these 4 4-dimensional matrices. But we need to reduce them down to these 4 2-dimensional matrices. So they have a similar form to the training and testing matrices that we used in deliverable 4, where we have features on the columns and observations on the rows. What are the features that we have now from our gesture data? We had 4 features to describe the flowers. If I or your ASL student signs something, and you want to try and predict what they're signing, how many features do you have? And what are they?
120.
120, exactly, right? So instead of 4 columns like you have in the flower data set, we now have, same thing up here, we have 120 columns which represent each of the 120 numbers that represent a single gesture. How many rows do we have? How many instances of the digit 3 does my computer have at its disposal? 1,000, right? So we now have 1,000 rows, which correspond to those 1,000 frames of me signing the digit 3. How many columns here? Or sorry, how many rows here? Same thing, right? We have another 1,000 of when I did it again of me signing the digit 3. Same thing over here, right? We have 120 rows. Of this data, and again, 1,000 rows. Okay. Over here, if you'll remember back to our iris data set, each row here had a digit either 0, 1, or 2 associated with it over here. We don't have our y's yet over here, but we can make them. So in phase 2 of Deliverable 5, you're going to create a matrix, a vector here. So a vector has 1 column. How many rows is this vector going to have? 1,000, right? And what are the numbers that you're going to store in that 1,000 by 1 vector that's associated with this matrix? What? 3, right? You're going to have a vector that just has all 3s in it, right? Because each row here is storing a 3. You're going to have another 1,000 by 1 vector associated with this training matrix. What numbers are going to be stored in that vector? 4, right? All 4s. Another one here, which is all 3s, and another one here, which is all 4s. My hand's getting tired, so I'm not going to write all those. But you get the picture, right? Okay, so we've talked about step 1, which is record all the data. Step 2, which is reduce these 4-dimensional matrices down into 2-dimensional matrices, because that's what KNN digests. It can't digest a 4-dimensional matrix. It expects all of its training and testing data to be presented in a particular form. Give me a 2-dimensional matrix where the columns represent the features and the rows represent the observations, and also give me a vector which stores integers which represent the class that those observations belong to. Okay, step 3 is we need to provide this information to our KNN so it can distinguish between 3s and 4s. How do you think we do that? We have 2 training matrices and 2 training vectors. When you trained your KNN in Deliverable 4, you just had 1 training matrix and 1 training vector. How are we going to combine these to make it digestible for the KNN algorithm?
You just append them and have it 2,000?
Exactly. You're going to append them or stack them. So you're going to take these 1,000-row matrices and just stick them on top of one another. So now you're going to have a single 2-dimensional matrix called train uppercase X. And that single matrix called train uppercase X, how many rows and how many columns is it going to have? Exactly. 120 rows, 120 columns, and 2,000 rows. We're going to take our 2 vectors, this one that just contains all 3s, and this one that contains all 4s, and do the same thing. Stick one on top of the other, and we now have a 2,000 by 1 matrix where the first 1,000 elements contain the number 3, and the second 2,000 numbers contain the number 4. Now we have one matrix and one vector. Give it to k and n, and you've trained k and n. We do the exact same thing with our testing data. We take our 2 testing matrices, stick one underneath the other, take our 2 testing vectors, stick one under the other, and give that to k and n, and we hide the vectors. It can't see them, right? And it's got to make a prediction. Does this row correspond to a 3 or a 4? Does this row correspond to a 3 or a 4? Does this row correspond to a 3 and 4? And so on. And we're going to see the percentage that it gets right.
There's a lot of data. Is there going to be any resource problems with this, Kevin?
The resource problems mostly are visualization, right? KNN is actually is called a weak learner, which we talked about last time. It's the most obvious of all the machine learning algorithms. It's trivial because it's really just taking one row and finding the one that's closest. That takes a little bit of computation, but it is much, much less compared to the real-time drawing that you've been doing to the screen. You should not be running into any resource issues. Okay, any questions about that? Pretty clear what we're doing? Okay, just a couple of other miscellaneous points I want to make about Deliverable 5. There's been some issues about NumPy save and load. So in Deliverable 4 and 3, I think I asked you to use NumPy load and save, and some people were having problems with that. We're going to switch over from NumPy save and load to pickle dump and pickle load. Everything we do from now on is going to be pickling and unpickling. This is super important because you're going to be uploading these 4 matrices to us at the end of Deliverable 5. That's what you're submitting. And we expect that all of these matrices are pickled, meaning you stored them to your disk using pickle dump. And pickle is a fantastic package. I told you were going to use 4 packages in this class. I guess I lied. There's this 5th one, pickle. Pickle is fantastic because it will take any data structure, matrices, vectors, a hierarchy of objects, and it will pickle it and store it to a file. And you don't need to worry about how it was formatted to be saved out. If you call pickle load on it, it will give you back a data structure in exactly the same form. So if I write a new Python program called train3 equals pickle.load, and I put in that file name, train3, it will store in this variable called train3, I will find 1,000 by 120 two-dimensional NumPy matrix. For those of you that programmed before pickle exists, this is like magic. You used to have to do this all by hand, figuring out how to save everything to a file and write additional functions that would read it in and put it in the right format and so on. Pickle says, whatever your data structure is, I'll pickle it and put it to a file. If you still use pickle to bring it back using pickle load, it's in the same form. This is super important because we're going to combine all of your data sets, so we expect all 4 of your matrices to be stored using pickle dump. After next Monday, when the TA has got all 37 data sets, 37 times 4, it's got from all 37 of you all your 4 data sets, he's going to combine them into one big tarball, one big file that contains all of our matrices, and it's assumed that they're all in the pickle format because you are going to start loading in each other's data sets. We ran into this problem last year. Some people use NumPy save and load. Some people use pickle. I think we're clear, right? Everyone is going to pickle and unpickle from now on. Good? Okay. Let's see. Okay. One other note I wanted to make. Let's see here. Yes. Okay. Okay, starting on step 36 of Deliverable 5, you will have already created these 120 by 1,000 matrices, but we are going to try and reduce them further. We're going to try and compress our numbers a little bit because there's a hidden problem in machine learning, and this is actually the biggest problem in machine learning, known as overfitting. Overfitting happens if you have many, many features and relatively few observations. If that happens, what often a machine learner will do is instead of trying to look for a common pattern in all of that information, it will just memorize things. KNN is not really looking for a pattern because it's just looking for the k nearest neighbors. But we can make sure that our learner does better if we reduce or try and compress the number of features. And it turns out that these 120 features are actually redundant. We don't need all 120. So if you look at your own hand and you start moving it, you can actually start to figure out what are some of these redundancies. So your KNN learner is eventually going to try and figure out which of these 10, if any, the human learner is demonstrating. What do you think is redundant in there? We want to try and reduce this 120 down to fewer columns. Makes things easier for our learner. Which of these features are redundant?
Wouldn't like the base be redundant because it's always like
The bases of the four fingers, you're actually pretty close, right, are what? They're always the same distance from one another, right? I can't pull the base of my index finger away from the base of my middle finger. There's a constraint there. There's a lot of them. We're not going to build that one in. There's some others.
Is it that, because there's 4 bones that it builds in, it's that first bone that you can't really change?
That is true for the fake first bone in your thumb, because it doesn't exist.
Yeah.
You're getting close.
At the beginning and ending of the bone, which is the same.
Exactly. Think about it, right? So the tip of my middle bone, the intermediate phalanges, has exactly the same 3D coordinates as the base of my distal phalanges. So you can find those 2 rows in here, and if you actually pull them out, in NumPy you will see that those sets of numbers are exactly the same. So we can throw one of them away. That's another one where we didn't build in, but you can also put that one in there. What else is redundant? Actually, that's a big one, right? That gets rid of a lot of these 120 columns. Take your index finger and try and bend your distal phalange, or the tip of your index finger, but do not bend your intermediate and proximal phalange. Please don't actually do it, or we're going to be rushing you over to the College of Medicine over there, right? You cannot. They move together. If you take the position of the base of this finger and the tip of this information, you can actually figure out what all of these other positions are. So some of the information we're going to throw away is information intermediate to the finger. So you're going to throw away everything except the base of the proximal phalange, the base of this finger, and the tip of the distal phalange, the tip of this finger. Everything else in between is correlated with those 6 numbers. You cannot physiologically uncorrelate them. Okay, one of the fun things you can do if you get bored while you're working through Deliverable 5 is try and figure out some more of these constraints. Okay, the only one we're going to throw away is that one that I just described for now. Once you get data from everywhere, I want to make sure that everyone has the same shaped matrices. So you're only going to do that when you collect everybody's data for Deliverable 6. You can reduce further everybody's data if you want. It's optional. Make sense? Okay. One last point I want to make about Deliverable 5. Here we go. Okay, step 40 here. I told you that you're going to be trying to record data while you rotate your hand so that we get training data from different orientations. People are also going to differ in terms of their position, right? So if this is leap motion here and somebody sees the digit 3 flashed up on the screen, they might do this. Or they might do this, or they might do this, or they might do this. So the test data that you get back while your program is running and KNN has to try and figure out, is this a 3 or is it something else? We want to try and normalize for position. We want to make sure that the KNN algorithm doesn't care what position somebody signs a digit at. KNN hopefully will not care about the orientation because you've already given it lots of different orientations. I could have also asked you to move your hand around, but it turns out that we can normalize for position super easily. You can kind of see the pseudocode there, but what's the intuition behind conditioning this data so that it's robust to position? So you get back, let's say, here's my leap motion device. I sign the digit 3, and you capture those 120 numbers. What do you do to those 120 numbers? Average them. It's part of it. Take one of them and make it 0, right? So we're going to go through those 120 numbers, and you're going to slice through your matrix and grab all the x coordinates. Hint, that's the first and the fourth stack, but you can figure it out from here. We grab all of those numbers, take the mean, we take the mean of those numbers, and then we go back and store back into that 4-dimensional matrix, we subtract the mean x value. So in essence, what we've done is we've taken a whole bunch of frames and we've moved all of them so they're at the origin, right? So somebody may have signed the digit 3 to the right of your leap motion device's field of view, but by subtracting the mean of x, you pull it to the center, right? So we do that for x. You're going to do the same thing for the y coordinate. So if people sign the sign at different heights, you're going to normalize by y, pull everything down there. And if people sign at different z coordinates, we're going to pull all of those at the center. So at the end, the data that you save out, it's as if people had signed everything at the origin, but with different orientations. So that will, fingers crossed, make your KNN learner robust to orientation and position, but not robust to some of the other differences among the 37 primary hands in this room. Right? We'll get to that later. That takes us to the end of today's lecture. You will have a quiz about what I just described about Deliverable 5 for tonight, and we will eventually move on to Lecture 6 on Wednesday. Thank you. I hope you enjoyed the toffee. No problem.